it's time for the next presentations. And I warmly welcome you to the session about embedded vision. And within this session, we have 3 presentations planned. And we will begin with the presentation from Mr. Horst Mattfeldt from the company Matrix Vision, who will speak about embedded vision, what was, what is, and I think most interesting, what will be. So, Mr. Mattfeldt, please come in front. The stage is yours, and we are looking forward to your presentation.
So, this is the, okay. Hi. As Paul already mentioned, my name is Horst Mattfeldt, and for this almost epic theme, obviously the company decided to use the oldest, most senior consultant they could find, and that's me. Okay, what will be, who knows? But let's start with what was. And if that works correctly, this is the company presentation which must come. Just a few figures at a glance. Matrix Vision was founded in 1986 already. In 2007, we were bought by the larger company Baluf, who is now our beloved mother company. We have, thanks to Baluf, 68 branches spread over the world. And we can possibly configure 80,000 different camera types and models based on our modular concept. From that, we ship more than 50,000 components per year. And in total, this is done by 120 employees working hard for your applications. So the portfolio overview shows what we can do for you. We have a large portfolio of industrial cameras. We have smart vision. We have 3D machine vision. We come from OEM business and from the customizing business. We do software, and now we are talking in depth about embedded vision, what that is and what it was. Embedded vision, Matrix Vision was probably known since the beginning for their intelligent cameras, and we call them intelligent because that was originally embedded vision at its best. A sensor combined with a processing power in a small housing, running whatever applications you can think of. A nice example for an edge-based application which we solved 12 years ago is this picture. It shows a dual head stereo or day-night system based on a Power PC that was at that time the latest, greatest, which you could find. And because at that time a Power PC was not strong enough to do an OCR based on this module, we made an FPGA-based license plate reader, and now you see where the application comes from. It is a license number plate reading application for traffic safety. And we only send the area of interest of this license plate to a server which does the read then with the best algorithms which you could think of. This is an edge application 12 years ago. No one talked about embedded vision, so we are still in the history. In the meanwhile, it looks like, I mean, it's not absolute safe data, but it's a relative data. And we could think of our business as that we are a free rider of technology. So you could think of machine vision that we are a free rider of PC technology. And if you see this graph, the graph prints the performance for a laptop computer based on a Core i5. The source is also given from where we get this data. And there you see the performance is not increasing as the Moore's law could think of. So it seems that the Moore's law is slowing down a little bit for the Intel or for the x86 world. Whereas it seems, or you can look at the ARM compute stuff, and clearly for embedded vision, we are a free rider of the mobile phone and the mobile computing applications. That means we take what they offer and we do our best in making embedded vision applications for them. And at least Apple and NVIDIA believes that their performance graph is that way. That means they are accelerating, and at least in some areas they are better and faster and more performant and consume less power than an ordinary PC. So that's what happens meanwhile 12 years ago, and so this is now going to happen. So we are the free rider in technology in general. What happens right now is that, and if you see these core figures from Sony sensors, you can see that the performance of the Sony sensors versus generation increases in terms of resolution and also in terms of frame rate. That means you need interfaces which are fast enough to take the data and send it into the memory of the processing unit, regardless PC or embedded. That means the resolution goes up, the frame rate goes up, so the bandwidth requirements go by the multiplication of this. That happens in the meantime. Here, as a figure, if you have a fourth generation 12.4 megapixel sensor, you can run it at 175 FPS. That's a lot of data which you have to manage. If we take this data and we put the bandwidth requirements versus what the interfaces achieve, you see that the established interfaces offer what Sony sensors need. And in the middle, in the light blue, we draw what PCI Express as a generic computer interface can offer. And there you see PCIe Gen 3 times 8 is at the topmost of the graph. It's even outside of the graph. That means if you take PCI Express as a base technology, you are fast enough for everything. Not everything, should not say that, but for most of the applications. So that's why we choose PCI Express, of course, which is ideal for embedded. I would not say this is good for a 100-meter distant camera application. For embedded, close distance, it's very ideal. Why? It's ideal because PCI Express gives you a high scalability. Scalability means that you can choose, I take one lane, and I take 4 cameras then instead, or I take 2 or 4 lanes and take 2 or 1 camera instead. And basically, you can make such arrangements, and in combination, you can transfer, in general, 400 megabytes per lane at the most established generation 2 interface, which is available. That means we can transport, and this is the brutto data here, we can transport almost all data what the IMX sensors will offer us now and in future. The advantage of PCI Express is you directly write into the memory of the computer, or you can directly write into the graphics memory for doing CUDA applications or whatever. That means you have the lowest possible overhead in terms of CPU load, latency, and whatever you can think of. So PCI Express was our high-end embedded data path. Now we show you the product presentation. We offer a family of products. Currently is the NAOS 2, and the features are, it's really small, it is industry standard compliant. There is if you have an application which is using Genicam, GenTL, you can immediately use that with this camera. No need to change things. It's very efficient. Just as a rule, you have 4 times the performance of USB at the power consumption of one USB 3 camera. It has the lowest latency because we don't have a memory in between. We just write the PCI data into the main memory via DMA. No CPU interrupts, nothing. Therefore, we have the lowest CPU, GPU load, which you can see. And the advantage of PCI Express is it is available for various system on modules or system on chips. That means you are not restricted to only ARM, only Intel. You can do whatever you want. And you can do it under Windows because you are used to, or you can do it under Linux. The nice thing about that is, and we heard that in the session before, due to the fact that the data is immediately in the memory, you have access to all artificial intelligence frameworks and most of the accelerators which are on these SoCs available. So you have the choice. And of course, as I mentioned, you can connect more than one camera. Because this is not so often used, we give support for custom carrier design, because ideally this one flex connector takes all the data, inputs, outputs, power, RS-232, all this, and we give you support for a carrier board design. In detail, the NAOS 2 family gives you from 1.6 megapixel running at more than 220 frames a second, up to 24 megapixel, and here the Gen 2 12 megapixel runs at 64.6 frames. And keep this number because you see what improves with what comes next family. So we offer a large family, and here you see most of these figures are outside of reach of other technologies, be it USB 3 or MIPI or whatever. So usually this cannot achieved with lower end technology. Having said that, one important embedded vision player is NVIDIA, and we have tested, and we also show on our booth applications with these. And our cameras are compatible to all these mentioned nice, call it supercomputers, or relative to their size and performance and power consumption, they are really highly efficient in supercomputers. So the camera is ideally targeted for that, but that's nothing special. Everyone here on the Vision Fair tells you that they make something for that. But our cameras also work for the embedded architectures which use Intel or x86 computers. On the left-hand side, you see an example of the COM Express. The most left picture is the system on module COM Express. And on the right-hand side, we show a SMARC, which is another standard Intel x86 architecture. So the cameras can be immediately used with that. For people who are not sure that they want to go to ARM, they can take the same application and camera and do it in this way. So an outlook for what comes next. Coming next is the NAOS 4, optimized for the 4th generation of Sony EMX sensors. And now we achieve a pixel performance of 1.5 gigapixels, whereas the NAOS 2 can only deal with 800 megapixels. So the interface is 4 lanes PCI Express. And then we have in detail the performance which you can see here, and then the 12 megapixel sensor runs at 104 frames per second, and the 24 megapixel runs at 55. So what will be? That's one possible way to go with the high-end applications. And what also is an area where we work on, we are looking forward to the standard EM Vision, because in our thinking, the Blue Naos family is GenICam, GenTL compatible, but currently we are lacking some low-level. What we will do. So we are lacking some low-level standards, and this is an area we are working on. That means it can get even easier in the near future with that. And last but not least, the EMVA launched this EM initiative in 2019 for an EM Vision standardization, embedded standardization. Latest, for me personally, I enjoyed the last 11 years at Matrix Vision. This is my last presentation at the Vision Show, because I hope that I can enjoy my retirement. Thank you very much.
Okay, Mr. Mattfeldt, thank you very much for the presentation. What was, what is, and what will be. Great overview.
Thank you.
And we will now go on to some questions. One question is, can you give a recommendation? Will GPU outperform FPGA, or will in future high-performance application will have both of each world? Can you give some kind of recommendation on that?
I would, although I'm not 10,000% deep in this applications, but I would say, because of the fact that a GPU is available and you can use that for CUDA or for the OpenGL stuff, I would always try to use that because it's available. If it is not strong enough, I would probably search for an FPGA-based stuff, but in this order, not the other way around. My guess. I know that some people treat that differently, but that's my thinking about that. I would always use what is there and make the best out of by combining things cleverly. It's very often, don't try to reinvent things.
Okay, thank you. Thank you for that recommendation. And Vision community wishes you a good retirement. So thanks.
Thank you. Sit down.